Alright, let's get started with the next problem of the day. This is going to be LeetCode number 787, sorry. Cheapest flights within K stops. Funny number, 787, Boeing. Yes. Anyways, there are n cities connected by some number of flights. You are given an array of flights where flights I is a triplet, which indicates that there is a flight from first index to the second index with cost, which is the third index. You are given three integers, source, destination, and k, and return the cheapest price from source to destination with at most k stops. If there is no such route, return -1. Okay. Let's see. Are there negatives in here? The price is between 1 and 10 to the 4. There will not be multiple flights between two cities. Okay. And the flight's length is between 0 and n times n minus 1 over 2. I guess that means that the number of edges is at most n squared, or the number of nodes. Okay. Looking at this problem, looks like the idea is that we want a single pair shortest path between two cities within k stops, or the single pair shortest path between two nodes with traversing at most k edges. This seems like a job for the Dijkstra's algorithm. At least that's what I'm feeling so far. Dijkstra's is a greedy algorithm which relies on a heap to find the current shortest path, investigate it, and see if there is a viable path to a certain destination. Of course, Dijkstra's does not work if the path has a negative, if any of the paths have a negative weight, in which case we'd have to use some other algorithm. So, I think this might be the first actual instance of LeetCode where I've been tasked to implement Dijkstra's. Exciting. Anyways, let's actually start talking about this. And so, first application of Dijkstra's algorithm. Exciting. So the idea is pretty simple. We have a heap of flight data. And I think in this case what we will need is our current city. We will need our current price. And we will also need we'll also need our paths traversed so far. And let's see. We'll also need a hash map of this hash map will contain cities that we can traverse to, given a source city. So this will be a mutable map of integer to int array, right? So the key is going to be our source city, and the int array will be an array of all the destination cities that we can get to. Actually, we'll keep it as a list of int, Because of course we don't know until we actually add all and traverse all the possible flight edges, right? So, and we'll also need for Dijkstra's, we will need a set of visited cities. In some data structures and algorithms courses, this is also called a cloud. Up to you what you want to call it. It's essentially a set of cities that we visited so that we don't go back to them and reinvestigate them. The idea is that once a city is added to the cloud, we have explored all possible options or have them added into our priority queue, and therefore we do not need to further investigate them. It could be wrong though, it's been a while since I've done Dijkstra's algorithm in really any capacity. We'll start by adding our start city, and let's see. Ooh, I just realized. Maybe this will be a list of int array. The idea is that int array 0 is city, int array 1 is price. Of course, we need to keep track of the price somehow. We know that each path will cost one path towards our k stops, but yeah. So we'll start by adding our start city. So that'll be start with and then we will say for each element within or for each city that we can add into our, or add all of the cities assuming they are not in the cloud to our heap organized by price. And let's see. Okay. Well, out of all of our cities, assuming that they are not in the cloud, into our heap, sorted by price, then we will add our current city into the cloud, and we will repeat until we exhaust our heap or until we've reached the end or the city. And of course, if we are at k, or if the current city number of stops is already k, then ignore the city entirely. And the idea is that if we've reached some city which is not our destination city, and we've already hit k, then we don't care because we cannot take this path from this city to any other city that is needed. What I'm thinking right now is whether or not Dijkstra's is actually needed. Of course, it is possible to have a cycle within this graph, but I'm starting to wonder whether or not it could be possible to simply exhaust search domain, I guess you could call it, using something like a breadth first search. And I'll think about it some more, but I think I'll stick with the Dijkstra's type deal for now. And we repeat until we exhaust our heap or until we've reached the destination city. And this will run in the Dijkstra's algorithm runtime, which I've forgotten already, which is probably not a good sign. It's got a log in there. It's like, okay, let's see if the heap, well, we can only have as many as log of v operations, and we say we traverse all the edges, so e log v. I feel like I remembered that there was a square somewhere. I don't know. Definitely something to keep in mind. So to do, take a double check at the runtime and space complexity. In any case, let's go ahead and get started by coding. Let's see. So we'll need a destination price map, which will be a mutable map of integer to a list of int array. We'll need a visited cities, which will be a mutable set of integer. Then we'll need a candidate cities, which will be a heap. In this case, this will be a priority queue of integers. Well, not a priority queue of integers. We will need to create our own. Let's create a data class, candidate city, which will have a current city, which will be an integer, a val price, which will be an integer, as well as a stops counter, which is an integer. We'll need to create a new comparison. So class candidate city comparator, which will be extension of comparator on candidate city, or implementation of. And we need an override function on compare. This is going to be first, which will be a candidate city, and a second, which will also be a candidate city. This will return an integer. And in this case, we can just return if first dot price is less than second dot price. So this will be a priority queue of candidate city. And I think we need to initialize this. Let me just double check. So this is a priority queue, which takes a comparator. So it will instantiate it there. And we'll add in a new candidate city, which will be our source, with initial price 0 and initial stops 0. And we'll say while candidate cities is not empty, don't remember if is not empty is a thing within this collection or if it's a Kotlin specific thing. Yep. Looks like that mosquito or fly or whatever still running around. Anyways, we'll say val current city is equal to candidate cities dot poll, and then we can say destination price map for each. So this will be going through each destination with price. Let's see. If destination with price at 0. If our set does not contain this destination, then visited cities or candidate cities dot add. This will add in our destination with price of 0. Well, we need to actually create a candidate city with that, and then our price will be our destination current city dot price plus destination with price 1. And then our third attribute will be current city dot stops plus 1. And then at the end of this, we will say visited cities dot add current city and of course we're going to need a variable to say to calculate our current price point. So price to destination is equal to, and we'll start it off at integer dot max value. And let's see. With Dijkstra's algorithm, assuming that we actually run it correctly, I believe there's a guarantee that the first time we encounter our destination, it is actually the lowest price, or the lowest weight, if I recall correctly. So in that case, maybe we want to say if destination with price 0 is equal to our DST, then we return our current city dot price plus destination with price 1. Well, if it contains this, and, well, if current city dot stops is less than k, of course, then we want to do this. Otherwise, just add it into our scene, our visited cities, and ignore it. I do wonder, though, if we end up in a situation where if there is a city that we visit, which we visit sort of, if there's a city, let's say out there, city J, starting from city I, where we have a super long number of routes to J, but it's the cheapest route. But we also have a single route, which is expensive as hell, which goes directly to J. And let's say that we have to get to K. In that case, our algorithm would go all the way to j, and let's assume that that's actually the shortest route to k, or to j. And it'll say, okay, by the time we get to j, we've already exhausted our number of stops, so we can't make it for any further, and so we mark that node as seen, and we return -1. That's not actually what we want. So while we do want to optimize for our price to destination, we also want to make sure that if we've hit the number, our sort of limit on that, it actually doesn't really matter unless we've actually properly visited it. Unless we decide to properly visit it and actually consider all the stops. Of course, I wonder if there is an example of, well, we remove it anyways, and if it's not less, then we'll eventually exhaust our candidate city heap, so I guess that's not a big deal. I was gonna say if we might run into an infinite loop, and maybe we still, but perhaps not. So we'll say for now that it's like this, and at the end we will do return -1, assuming that we could not find a suitable city. I'm still operating under the assumption with Dijkstra's that the first time we encounter our destination city, it will be the cheapest price, because that's sort of the whole thing with Dijkstra's is that you're running a greedy algorithm with a heap that guarantees, as long as you have non-negative weights, that you will run into your destination first with the cheapest weight possible. At least that's what I'm assuming right now. Could be wrong. In any case, the last thing that we need to do is actually fill up our destination price map. So we'll say for, we'll say, let's see, flights for each. Flight, I guess. If destination, or we can say destination price map dot put into our flight originates at our first location, and we would do let's see, let's make this a mutable list. So we'll say if destination price map at get flight 0 is equal to null, and if it is null, then we'll say destination price map. We want to put into at flight 0 a mutable list of int array with a value of a new int array of, and we'll say flight 0 or flight 1 and flight 2, which is the price. Otherwise, we'll say val list is equal to a destination price map. I just realized I did pug. Get at flight 0 as mutable list of int array. And we want to add to that list an int array of flight 1, flight 2. So this populates the destinations of the given a source city with its accompanying price. We can add you up here. And we do on the candidate cities. So let's see. At most case stops, one thing that we should also consider is what is considered a stop. in this case, the number of stops is really the number of stops in the middle, right? So we only really consider that the one in the middle as a stop. So yeah, so if we're at any value less than k, then we're fine. Because the last arriving at the destination does not count. So I guess that's pretty much it. Let's take a double look. So we create a map of our destinations with our prices, a set of visited cities, a priority queue of candidate cities that we've filled out. We populate this destination price map. Then we go through our heap. We search from the cheapest city. Excluding our source, we start at the source no matter what, but after that, all the cheapest next city. We look at all the destinations that we can fly to given there, assuming that our number of stops has not been exceeded. And we check and we add them into our heap. We add them with the candidate city, with the actual location that we're flying to, along with our current price plus the new price to get to there, as well as adding 1 to the number of stops. And at the end, we add our current city to the cloud so that we don't visit it again. This is pretty straightforward, and if we reach the destination at some point, as long as we're under k, then we can return that amount. Let's see. Does this work for a direct flight? That's a good question. If we start on a particular item, and let's say that our k is 0, so we can only take direct flights. Then we take our first city, and since our number of stops is at 0, then it's not less than k, and even if we had a direct flight to there, it wouldn't count, and we return -1. Okay. So maybe in that case, we want to move this down, actually, and say that this only covers the case where if we are actually in here, if we are actually trying to add a city, which is not in the cloud, then we need to make sure that our current value is not, our current k value has not been exceeded yet. So that then begs the question of whether or not our current city adding it to the set is correct. Because if we, again, the idea of if we traverse all the way, because that's the cheapest route to some value j, and we hit our value k, our limit on number of stops, and we can't reach our end, but there's a cheaper route there, then will that be a problem? Let's see. I think so. I think that'll still be a problem, but how do we solve this then? Do we just move our visited cities into here? Could be an option. And we add it into our set there. But will this cause an infinite loop then? Will this cause an infinite loop? If we don't add some particular city into our visited cities, let's see. Let's take this example for a spin. If we started there, let's see. Let's say our k is 1. Well, what is this logic actually really saying? If our current number of stops is less than k, then we add some new city, and then we also add it to our list of visited cities, our current city. I feel like this should work. Is there a situation where we don't add, or not that we don't add a city? Well, actually, yeah. So if we don't add a city, then we just don't. Right, so not much has changed. Sorry, I got interrupted there, and I think OBS crashed or something. But we brought back the lowest price because it's the first time we encountered this destination city. It's not necessarily the cheapest destination, or the cheapest route, rather. For example, this when we start at 0, even though we encounter 2 right here, actually going through that route is not the cheapest. So we need to record the lowest price that we've seen so far. There's probably a more efficient way to do this, and I'll keep on taking a look at this afterwards, but that's the main thing. Again, the core of this problem is that because we're looking for the cheapest route with regards to weight, we can use something like Dijkstra's in order to achieve a pretty decently fast runtime. In any case, I hope you learned something, and I'll see you for the next problem.